So welcome to the pre-recording of lecture 40 of Introduction to Computer Science. So this is the 20th session of this course at the very end of the 7th week, the second half of the 20th session. In the previous lecture, so the first half of the session, we introduced sockets. Sockets are the means by which programs communicate with each other and by which we can do network programming. The purpose of this lecture is to illustrate how this can be applied um, to do high-level parallel processing. Um, we have earlier, very long time ago, we have covered Monte Carlo simulation. So this is an example of a pleasingly parallel computation where there is very little communication overhead between the processors. One needs to be careful that, however, every simulation uses a different sequence of random numbers. So the server is responsible for accomplishing this. Python exports the multiprocessing module. Python is a framework language with a lot of classes, so there will be a class to essentially make an abstraction of a process. This is very useful if you want to have everything defined in one single program. So with sockets, we have already seen the tools of implementing a parallel program, but with the multiprocessing module, this will be um, much more convenient to program. So we'll use the estimation of pi, which is actually a very bad program, but it's a good computationally intensive way of working, good for observing speed up. And there's also the notion of quality up. If we can afford to wait the same time on a computation, how much better can we compute if we have more computing power? All right, here is Monte Carlo simulation again. Pi, the pi, so here you see a circle, you can think about a pi, but pi is the area of a disk of radius 1. So it's a transcendental number. Decimal expansion goes on forever. So the way to estimate pi can be explained in 3 steps. We generate random points in the unit square. We count the number of points that are lying within the unit disk. So the distance to the origin is less than 1 or equal to 1. And because we were working with the square 0, 1, 0, 1, we have pi over 4. So our estimate is 4 times the ratio of the number of successes over the total number of experiments. So we will illustrate this with 2 clients. So this is in the client server module. So this is a pleasingly parallel computation one expects for an optimal speedup. Speedup is often prevented when there is a lot of communication overhead and synchronization needed between communicating programs. Here there's only one communication at the very beginning. The server distributes the seeds to the computing clients, and at the end the clients send back their estimate to the server. The server averages then the computations. So almost all computers are parallel, so even a simple laptop you should be able to observe a speed up of 2 if you are using 2 clients. Okay, what is important here is that even though this is a very useful computation, in general simulations are used to estimate high dimensional integral in order to compute expected values. It would be utterly pointless and meaningless if all the processes would start computing the same random sequences. So this is not within the scope of this course, but random numbers on a computers are not really truly random, so they behave to us as if they are random numbers. So one needs to be a little bit careful. So we're going to take careful a little bit of this as well, and that actually makes our computation entirely deterministic. Client number one will receive seed one, client number two will receive seed two. Um, Okay, some terminology. So Python exports in the multiprocessing module the class process. So a process is actually very similar to a thread, although we have seen in the previous session multi-threading. A thread is a lightweight process. A process can be seen as the equivalent of a Python program. So if we are using the multiprocessing module, we're going to actually launch many Python interpreters. So a process is the name of the class. So we make a process. When we make a process, the arguments of the constructor are two things. So they are the function that the process will execute and the value for the arguments. So this is how we can communicate between the main program, the main process that forks the sub processes. So in the terminology of multiprocessing, we fork a process. The process that is forked is called the child process. We can verify this with the operating system module. The process identification number of the child is typically larger and sometimes just the next number of the original process. So there is the join. That is then the parent process, the main program, will execute the join to wait for every other process, for every child process, the child process P here, to finish. So a process has data attributes, the function that it will execute, the arguments of the functions. There are two important methods on this object that's an instance of the class process, the start and the join. And that's, as an application programmer, that's all you need to know. Except that where do the client processes put their results? So you can pass the arguments. So common arguments in this estimation of pi are the number of samples, the dimensions of the computation that need to be done. The multiprocessing module also exports a queue. So a queue is also passed as an input argument. It's actually a reference, again, a reference to a queue, and every client can put the result of an execution of the function, can put in there. So the Python system will actually make sure that thread safety is guaranteed, so that when two processes simultaneously start to put elements to the queue, there will be nothing will get lost. The parent process can recover the results with the get. So we make a queue, so just an instance of queue. Putting something in there is with the put method. Getting something from there is with the get. And it is a queue, first in, first out. So that's the second class that we import from the multiprocessing module. First class being process, the second class being queue. All right, some terminology. So to recap, so the process class, we instantiate any object of that class with a function that every process of that class will execute. We can make as many objects as needed. So the socket communication that we demonstrated earlier, and that I will also demonstrate after the slide presentation, that actually required the execution in a terminal. And you can open as many terminals as you need and launch as many processes on a normal computer. This is fine, but this will actually not really scale if you want to use even already for 16 processes. It might be a little bit tedious. So that's also the advantage of the multiprocessing module. You can actually launch as many processes. First, make all the objects, put them into a list, and then to all the elements in the list, launch the start method, and then do the join method in a loop. Now, in the meantime, we have illustrated a simple manager worker module. So in the estimation for pi, the manager, the server, will distribute the seeds and collect the results. Every worker will actually receive the seed, also will receive the instructions that are needed to execute. So the workers are the child processes which will do the computation. So this is can be still seen as client server, but here actually we don't have a compute server. So typically you could have a very powerful computer, supercomputer even, that where people submit jobs to. Here actually the computations are outsourced to the clients. So there is the area also of volunteer computing, where people can donate their free computing time. If a screensaver kicks in, then the computer is idle and the computer can do some computations. So you can look that up, the issue volunteer computing. So this is a little bit similar pattern here, where the manager actually distributes the work. Estimating pi that way, it will probably go on forever. If you are using then also multi-precision arithmetic. All right, I will end with the notions of speed up and quality up. So parallel processing is extremely important. That's why we have it here already introduced in this course, because all computers, they have actually multi-core processors. They are also connected to the internet. You can have computers communicating with each other and in this way distributing the computational work. Speed up is the time spent by one process over the time spent by p processors. So if things go fine, you can solve the same problem p times faster. And often it can even go better because parallel computers, they actually have typically more memory and more also a higher bandwidth, but the availability of memory can also speed up there. So one computation that can achieve a better than p speed up is a lookup. If you, on average, you would expect that an element is in the middle, but it could be towards the beginning of a segment. So if you want to do a parallel lookup in an unsorted sequence, you let so with two processors, one processor takes the first half, the second processor takes the second half. If the number that you're looking for is closely distributed in the middle, then actually the second processor may have it quite soon and report defined much sooner than twice the amount of time. So that's an instance of super linear speedup. You can also think about solving a problem not so much faster, because a lot of problems are already solved within seconds. How can you then improve on that? Well, you can try to improve the results. So you can try to improve the accuracy. So having more decimal places in your computation. You can also be a little bit more severe on the tolerances in a numerical computation. You can try to do some extra checks. You can try to increase the reliability of your computation. So that refers to not solving only faster but also better. Or here are some exercises. So if you haven't figured this out yet, check now how many processors and cores does your computer have. So the next two exercises ask you to run the Monte Carlo and compute the speed up. We have seen an entire lecture on timing, or not an entire lecture, but we addressed timing Python programs. So this will come in handy here. You can also look for quality up in the Monte Carlo simulation. So you would expect that as a pleasingly parallel computation that with two processors, things go twice as fast. But you could also try to see how much accuracy can you gain if you let your processors do the same amount of work, so the same number of samples. Can you gain then additional decimal places? So define the quality up here. So the quality up, I gave here a very abstract definition. So the quality obtained by P processes. What is quality? Here now you can replace quality with the error. So we know we have a double precision floating point approximation for pi. You can compute the error, and you can actually see how much does the error improve. You can take the absolute value of the exponential format of the error, 5 decimal places versus 4 decimal places, or you can take the absolute value of the 10 logarithm or of the any logarithm and define it that way. So that's the exercise. Define the quality up for this problem. Okay, I have a number of scripts prepared. So in a way, this is demonstrating the socket module again. So I will scroll through a Jupyter notebook rather briefly because the Jupyter notebook actually is not so convenient and actually doesn't work for socket computations. It could be because I'm on a Windows computer, perhaps um, on others it works. So in any way, the Jupyter notebook is still very convenient for demonstrating small scripts. Here you see the code for the server. So what the server does, it defines its host name and the port number. So the clients need to know the port number. The buffer size, not so important here because also in this pleasingly parallel computation, the amount of communication is also extremely limited. So you see that the server will be waiting for two clients, first and second, so that these are the names of the sockets. So the server will be blocked when the clients connect. We've seen that everything that is, so sockets are used for communication between programs, and everything that is passed needs to be encoded as a byte string. So I'm making the byte representation of the seeds. The seeds for the random number generators 1 and 2, they are encoded. Then the server waits for results, and it will receive up to the buffer size a string representation, a byte string representation again from the first and the second. So these are the two parts of the approximation of pi. The strings need to be decoded into byte strings. So part 1 is a string now, by proper Python string. Part 2 is also a Python string. To compute with this, I need to cast that string into a float. So Python is dynamically typed, but it's still a typed language. Every object has a type. It's again very important that we know when to code in, so with the byte strings, and when to decode, and also when to cast. So when to take a string and cast it into a proper numerical type. Okay, that's the code for the server. Here is the code for each client, so it also fits quite neatly on the screen here. Perhaps let me scroll through all the way so you can see the close statements. So at the end, it's good practice to close the socket, similar how we close a file or a web page that we download for reading. So what does the client do? The client has the code in there. So this is the code that is copied from onto our Monte Carlo simulation for pi. Also, the number of samples is hard-coded. So 10 to the power 7, which is kind of a good number, 10 million. It will generate random numbers, and at the start of this computation, it will receive the seed through the socket. So it connects using the address family and the protocol. It connects to the server. Here we do everything in this course on localhost. We have to agree on the port number. So that's also what can go wrong. If you do this for the very first time, you will have to indicate, as I had to do on my Windows, that the port number could be used. That will require some firewall settings. By default, it could be on your computer that all the ports are closed. So you may have to do something for this. On other Linux installations, for example. So I want to emphasize again the encoding and the decoding, but now it is kind of mirrored. So the data that is received, I call it data because it's initially a string. It's good that the client confirms this. It receives a string. It casts the string into an integer. It will either receive 1 or 2. The seed is what is imported from the random module, together with the uniform random number generator. The client prints a message to the terminal window, so this is interactive, parallel, high-level processing. The client will send the string representation, so you cannot directly encode a number. So we can encode a string. So we take the string representation of the float, encode it as a byte string, and then apply the send method to the socket which will then be closed. Okay, I will demonstrate this. But so that works, but it's rather tedious. Instead, it's better to use the multiprocessing module. Here is the code. What this example will do is the hello world. So we had the hello threading in a previous session. We had the hello GUIs. We had the hello world in the very beginning of this course. So this is again um, getting familiar with another programming paradigm. So we have a main in here. So the code main is the main process. We will import the class process from the multiprocessing module. Every process will print a hello world and will then sleep for some second. So the argument that is passed, so there is here a main program. So we have a manager, a director, and somebody who orchestrates the computations. The creation of the process is very similar to how we worked with threads. So in a way, if you understood how threads worked, we are using the same mechanism here. In the main program, so let me scroll it up. In the main program, two processes are defined. By definition, when we make a instance of the class process, we have to provide the code, the function, the Python function that will be executed. We have to provide the arguments. And by the way, I'm talking about familiarity. If you go to a language such as C and work with pthreads, it's very similar. So you also pass but then a pointer to a function and you pass arguments. It's a little bit more complicated, but not that much. So similarly also to threads, we can make a process. So the process is born, then it gets ready for execution. The difference here, so the syntax is almost identical to threads. We use the process class, but the start and the join are the same. What happens, however, is entirely different. We actually launch another program, and it's actually the program that does this for you. In the first demonstration, I will show with terminals how to do this. As a user, I have to type for every process the Python. Here we will have two extra Python interpreters that will be launched upon the start. And then we wait for the join. So I should have indicated this with threading as well, but you have to be a little bit cautious. That's why the first exercise is important. Check first how many processors that are available on your computer, how many threads that you really have available, because you and also perhaps how much memory you have. Because if you go overboard, I would never, even on my computer, I wouldn't, which has 16 cores and 32 logical threads, I would not launch 1024 processors. That would completely swamp it. Nevertheless, we get to an application, the multiprocessing to estimate pi. It's still a bad algorithm, and in some sense, before you often consider using a true supercomputer, think about how you can use better algorithms. Think about how you can go to compiled code. In the Python world, think about how to vectorize your code with NumPy. But that's outside the scope of this course. Just an aside. Okay, here you see now the better implementation of the Monte Carlo. So I will import not only the process but also the queue. On Windows, I need to have this freeze support. That will kind of freeze the code for execution on Windows. I'm encapsulating the code that will be executed by every process in a function. So the function takes three arguments: the number of samples, the seed, and it will also take the queue. The queue that will be used here. The queue is actually not the name queue, it's the result. Um, So you see the code at the very end, it puts the result on there. So the functions have arguments, and the arguments are passed when each process is constructed. Um, all right, then the main program. The main program here illustrates that you can launch as many processes as you like, but I would not encourage to go much beyond 2 or 4. Um, this is an interactive program, purely interactive in timing. So if you think about the exercises, you may want to go to command line arguments. So we covered this before, so soon we will start reviewing in this course. In some sense, things are coming together. So if you want to solve the exercises 2 and 3, you actually should go to command line arguments, because you do not want to time the typing speed or the reaction speed of the user. Okay, so the main point here is also what we illustrated with threads. We can actually have a whole list of threads that we make. So here I have a list of queues, I have a list of processes. So it's important that every process has its own queue. So, and I will, in this list comprehension here, I will make instances of the class queue. So when we create a process, the function that is executed is the Monte Carlo for pi, and here you then see the arguments. That is the definition. The making of the processes, at this point nothing has happened. But then the forking of the processes starts. So the forking is not blocking, so this loop will just go through. For every process in that list of processes, we will apply the start method, and then the main program, the server here, will wait for all the processors to join. So every process will then put in the queue. So here the seed is the argument. The seed is again the processor number, starting at 1. Queues, they actually start from 0. That's why I have the k minus 1 there. So here you then see the list comprehension where the main program, the manager program takes the result from the queues and averages the results, and then prints the approximation and the error. The free support was critical to make this code run on Windows computers. It doesn't harm to put it on Linux, on other computers, but it is critical here. Okay, let me go to the terminals. So I will launch another terminal and actually launch yet another terminal because I will need 3 terminals next to each other. Okay, I can do it like this, but actually, well, perhaps it's not bad. So I have one server. The server is at the bottom, and I have 2 clients. So perhaps let me illustrate this. So this is not for practical purposes. This is to enforce what was covered in the first half of the section. So here you see I have launched the server. The server is waiting for 2 clients to connect. So I will launch the MC for pi, Monte Carlo for pi underscore client. The client is connected. So that was the first socket that was made. I haven't written a confirmation, so you have the impression that at the server side nothing happened, but the server has accepted the communication. So MC for Pi client, the same program. So I'm waiting a little bit in suspense because this is now when the action will happen. The second and next client connects. So you see that they received their seeds, 1 and 2. And 10 million is kind of a good number. Because for my computer, there is a delay, but it computes it rather fast. And you see already it's rather a stupid method to compute this, but you already have 5 decimal places correct. Okay, very good. So this is the client server explicitly coded with sockets. Not recommended, but good to give you a feeling of the complexity of the issues that are happening with interactive parallel computing. So there were 3 Python interpreters that were running on my computer and they communicated with each other. Okay, let me now run the more convenient way to do this. So this is the hello multiprocess. So what this code does, it generates, it forks 2 processes. So with the OS module, I can ask for the process ID. On Windows, on Linux, typically I see that the process ID of the child is typically 1 up from the main, but in Windows the numbers are more arbitrary. So I have created 2 processes, and 4 seconds and 1 second they pass up very quickly. So there was the starting of the processes, the hello from both process, they went sleeping, and then there was the main process in the main program that executed the join. Okay, so let me now illustrate the last script. So this is the MC, it's the multiprocessing for Pi. Oops. Multi-process. Number of samples, so 1,000, 10,000, 100,000, 1 million. 10 million was a good number. And I have 16 processors on my computer. So let's try to do this with that many processes. Now here you see I get 5 decimal places of this as well. And there actually are more processes running here. So that's actually the end. I can see the quality up, see how much I can do. I can also, so the seeds are actually fixed, so this will be a deterministic computation if I do this again. Yes, and this is more or less the conclusion of this lecture. So let me go back to the slides. So the purpose of this exercise is that you have some notion on parallel processing at a very high level. So it is possible to do with Python and to get some feeling for the single program multiple processors. So the program that was running is actually quite short, so I can almost fit on one screen here. So there is this single program that actually defines what gets executed by these 17 processors, by these 17 Python interpreters. So that's the main point. Parallel processing is an entirely extra course following this introductory course, but at least you get a taste for it. It also allows us to appreciate Python um, for an excellent prototyping language and how we can, at a very high level, with relatively little code, demonstrate the topics.